Thank you all for coming, 5:40 on Wednesday. And we're going to be talking about mutation testing, some case studies on Spring Boot APIs. So to start with, what are we really talking about here? What is the overall goal in general of any kind of testing? Generally, you want to make sure that your code that you've deployed works as expected, and that you can later on add some features without breaking stuff that you've already done, and again, that it's going to continue working as you expect it to. So today, when we're talking about mutation testing, we're going to be talking about even if you're doing test-driven development or code reviews or some other way of measuring your the comprehensiveness of your testing, you may still be missing some bugs. And that would be bad if you deploy them. So we're going to talk about how mutation testing works. We're going to talk about how to read the reports that are generated from the mutation tests. And then we're going to talk a little bit about how you can do this yourself if you're not already doing it. But first, oh, I forgot. Gosh, see, already. Two things. First of all, this is we have half an hour for this. It's a really interesting topic, and it's very tempting sometimes if people have questions, particularly to get really deep into the details of things. So we are both trying to guard against that. So if one of us starts to do it, we've developed a very subtle signal to stop the other one. If you see that, it's probably going to be me who needs to be quiet. Also, starting with our very first mutation, on the screen here we have a white cat with one blue eye and one green eye. And apparently white cats that have blue eyes are universally deaf. And apparently I'm not.
There you go.
I don't know. All right, I guess it's back. So if white cats have blue eyes, they are universally deaf, and white cats with green eyes apparently are not. So this cat, we suspect, may have just hearing in one ear and not the other. We don't actually know this cat, so we can't really say for sure.
And regardless, he probably won't come if you call.
It's not that strange a cat. So first, some introductions. My name is Heather Conklin. I am a senior developer. I work on Spring Boot APIs. Most of the time, I've been working with Java APIs. I've done a little bit with Python and Spark, which was really fun. About 7 or 8 weeks ago, I switched to a new team where we're writing in Kotlin. So I'm learning Kotlin. That's also kind of fun. I'm just going to talk loud. So if this thing comes and goes, whatever. I am a compulsive baker. So I bake when I'm happy. I bake when I'm sad. And it's really popular at work, which is great. And I haven't yet started baking when I'm angry, which I think would be problematic, but we'll see what happens. In my former life, before I was a developer, I was a certified financial planner for quite a long time. And I realized yesterday that next week is 4 years since I quit that job. So I'm so happy to have done that. This is way more fun. My personal mutation is freckles. I have quite a few of them.
And I'm Dave Kaiser. I'm a Java Kotlin Spring developer. I'm also studying data science and natural language processing. I am a former FBI translator. My language was Russian. Don't ask. I can't tell you the really good stuff. And my personal mutation is I only had 2 wisdom teeth on this side. Nothing over here. Not sure, but save me some money at the dentist. So why do we TDD? Well, trick question, especially in this crowd. You know this stuff. Reduce bugs, increase speed, match the requirements that you're trying to build for your consumers, and ultimately less stress, both because you can move incrementally and also because you have that trust that your test will catch you. So analogously, performers can take bigger risks. They can do grander flips or spins or twirls when they know they have a net. You as developers, you can take on a bigger refactor. You can move your code around. You can mess with the architecture if you trust that your tests are going to save you just in case. But, well, can you trust your safety net?
So no matter what kind of safety net you have, whether you're writing using TDD, whether you're doing peer code reviews or checking your code coverage, the people who are doing that checking, the people who are writing those tests are human. We're fallible, and we only have so many ways of thinking about problems. So mutation testing is a way of testing your tests to see how effective they actually are at solving all of your problems and catching all of the potential errors that you may have. Who does this? Generally speaking, systems that have a high risk of failure probably are, and if not, probably should be using mutation testing. So companies that are doing finance or insurance or biotech, apparently CERN, which is that large hadron, whatever it is, collider, they use mutation testing, which I think is good.
Don't want to blow the side off a mountain in Switzerland.
Definitely not. So it's based on two underlying suppositions. The first is the competent programmer hypothesis. So what this means is that the majority of defects in code are by competent programmers, so people who have some experience, and they're mostly little things. They're syntactic errors, or they're typos, or spelling problems. They're not necessarily large logical problems. They are things that most developers are getting things almost right. The second foundational idea is the coupling effect. What that means is that small defects in code cascade to create large problems. And if you can find the small ones, you have a higher probability of stopping the large ones. There's a whole body of studies that reinforce both of these things, particularly the coupling effect. So mutation testing, this is how this works. So what mutation testing does is it starts by running your test. It's going to be comparing your code against your test, so it has to know at the beginning that all of your tests are passing. And so it starts running the test, and then it takes your compiled implementation code and starts changing it on you. So these are some examples of some of the mutations that might occur in your implementation code. Maybe a greater than sign becomes greater than or equal to. Maybe it becomes less than. Maybe true becomes false, or substituting one method call for another. If you have a void method, those methods might just be removed altogether from your code. There's a handful, I think 6 or 9 sort of default mutations that will occur. And with just those defaults, depending on the size of your code base, there's an infinite amount of ways that mutations could occur in your code.
So what does it mean? Well, this might be a typical life cycle if you're doing TDD for a dev. So you write a test, okay? You make it pass. Well, that feels good, right? I mean, we all like to see the green test. Yay, I made it work. Awesome. You run the mutation test, and it mutates the implementation, and your test still passes. So, your net doesn't work. So all of the walking back and forth on the high wire and all those flips, the net's not going to catch you if you fall. So what are the tools and requirements? Well, we're using pitest. That's one framework for doing this. The requirements are that the tests have to have the same result every time. I had a method in a toy that I had built that was it simulated a coin flip. So it would turn a Boolean, heads or tails, every time. And I ran the mutation tests over this, and it still returned heads or tails, despite the fact that it was the polarity on the Boolean was reversed, so the mutation test was meaningless. Now, if I'd written a test that was going to return true every time and it starts returning false, now we've got a problem. So they can be run in any order, and they can be run parallel. And so basically, we're looking at unit tests. What to exclude: integration tests, end-to-end tests, contract tests, performance tests, anything that would change the global state. And the main reason for this is that the mutation tests are going to run in the same JVM as your code, and that's why you can't do the integration tests. Also, and this is just a recommendation, don't run your mutation tests on scary code. So the docs say that it will just do these things in memory and will not persist it into your code base. And there are certain things we want to make sure don't ever happen.
Specifically, it says it should not be released accidentally. So, I mean, probably.
Probably. It's all good.
Okay, so the division that we work for has about 17-something APIs in it. We started out mutation testing, just 2 of them, one in Java, one in Kotlin. So to start with, our benefits API The initial commit on this was about 3 years ago. It has over 13,000 lines of Java code, and after we excluded things like the integration tests and the contract tests, we ran the pit runner against 456 of our tests. It took between 18 and 28 minutes to run it on the entire API, depending on other processes that were running on my laptop at the time. And we did this, both of these were done with the IntelliJ plugin, pit runner. The second one was a much smaller code base. This is the membership search API, which was spun off of another API about a year ago. There are less than 2,000 lines of Kotlin code in this one, and we only ran it against the 42 tests that were left after we excluded, again, all the integration tests and the contract tests and so on. And this took about a minute to run.
Okay, so what is it doing? So here's an example of what the report, a piece of the report might look like. Or I'm sorry, a piece of the description of the process. So we've got a couple different mutators working here. One is the conditionals boundary mutator. So this is just, it's a little thing. It'll take a greater than and turn it into a greater than or equals. Or less than becomes less than or equals, just to kind of test where the edges are and where they should be. Similarly, we have an increments mutator. So you might have a process that does a thing and then it, plus plus to some variable. Well, it just changes it to minus minus just to mess with you and see what happens. Similarly, we have the void method mutator. You might have a method and it just says, you know what, that's boring, we're not going to run that. So it doesn't run the void. We'll see if it still passes your tests. Similarly, we have the return vals mutator. So maybe it reverses the polarity on your Boolean, or maybe you are meant to return a long or an int, and it adds one, or subtracts a handful, or whatever that might be. It might return null instead of your object. We have a math mutator that might say, well, instead of a plus, we'll do minus, or we'll do times, or we'll do something else along those lines. And the conditional negate the conditionals mutator. So equals equals becomes not equals, or vice versa. Greater than becomes less than. It's all just different ways of playing with the code to see what we can do to create chaos, literally. So these are just a handful of some of the bigger, more common ones for a list of all the possible mutators. Pitest.org has that. Pitest.org/quickstart/mutators. So next, the report. So you run this stuff. And as Heather says, maybe it takes a couple minutes, maybe it takes up to a half an hour if it's a big code base. And you get 3 possible outcomes when you run these tests in your report. So first one is, and this is what the report looks like. You get a green bar. The mutation in the code caused a previously passing test to fail. So that's good. The mutant was killed, and you know that your test is protecting you against potential production problems. White means that there was a mutation done in a line of code that wasn't covered in a test, and you might want to look at that. So it's not good, it's not bad, it's just, yeah, you might want to look at that. We might have a problem here, there's no way to know. And then lastly, and you get this in red, so you pay attention to this, the mutation, we have a mutation in the code and your test still passed. So one of those things that we were talking about was changed in your code and the test still passed. So that's the bad thing. The mutants have escaped from the lab.
Okay, so what do you do about these surviving mutants? We didn't make these up. There's 2 specific categories. We added another one, but the one that we added is the one that we were calling noise. And noise is a flavor of the second category, which is equivalent mutations. We're going to talk more about all 3 of these. So some are noise, some are equivalent mutations, and some are real problems or significant issues that are in your code or in your tests. So we'll talk more about each of these.
So first, noisy mutants. Getters and setters. Maybe you have a custom hash code, toString equals method. These are things you may not test. So, I don't know about you, but I usually don't test my getters and setters. I don't test my equals unless there's a very specific reason for doing that. Builder methods often fall here as well. And then we got a fair amount of stuff. Check expression value is not null, or throw NPE when we ran this over Kotlin. And the great thing about Kotlin, those of us who work in it, it has so much null safety, but when all that's compiled and then we do the mutations, we can get some weirdness popping up. So obviously didn't see that in the Java code, but saw a fair bit of it in Kotlin.
So some of these the equivalent mutations, look at these as opportunities to refactor your code. So a lot of the stuff that we were defining as noise is dead code or code that never gets called. In that first API I talked about, the Java API, we had all these data classes that we didn't have the Lombok annotation on them. We had these custom hash codes and two-string methods. We never, ever called those. I don't know why they're there. We maybe should just take them out. Likewise, as Dave said, the getters and setters, I mean, that's not useless code. We kind of do need to have those in there, but we're probably not going to test on those. Look at any code that you have that only affects performance. And again, I guess the main thing to look at with these equivalent mutations is you have to actually be looking at the code. You can't really just look at the report and evaluate from there. You kind of have to look at them both. This is not a 30-second, oh, my code coverage is 94%. It's not that simple. Question?
Does it have support for leaving alone code that's generated or that's annotated with the @generated annotation?
I do not know
Good
the answer to
question, yeah.
that.
I don't either. Good question, though.
It may. I haven't seen that in any of the reading that I did, but it would be something to look into for sure. Yeah. So to go back to this, code that only affects performance, consider whether you're prematurely optimizing that and whether you should just keep that going or take that out. There's also code that affects only your internal state. And the only example that I saw of that in our reports, with the pit runner that we had for IntelliJ, it actually also mutated our test code, which I thought was interesting. I was not really expecting that to happen, but it did. And so we had one test suite that had only 2 tests in it. It was about an account blocker thing, and it had one test that set account blocker to block account number 1, and the second test removed account number 1 from the list of accounts to block, and then ran a test that said, hey, nothing's blocked. So the pitest removed that second part that removes the account from the list of things to be blocked. So when it ran the test that covered that block of code, that test totally still passed because it hadn't run the first test that put account number 1 in it. So, pay attention to context. That's obviously something that is changing the internal state of your code. So, I left it in there. The second thing, or the last thing I should say, is there's some things that will survive that are killed by logic elsewhere in your code, or that can't be killed. So that's what the heading on this says. Some of these mutants just can't be killed. So I'll give you an example of one of those. So this is one kind of equivalent mutation. I should admit that I lifted this completely out of a presentation that Henry Coles does. Henry Coles is the guy who basically maintains pitest.org. So he's amazing. If you can watch one of his presentations on this, he's very good at it. Amazing. Anyhow, so suppose you have some code that does some logic. It takes an integer, and if the integer is less than or equal to 100, it's going to throw an exception. And if it's greater than or equal to 100, it's going to do something else. So mutation testing is going to look at this code, and it's going to, let's just say, mutate that last if statement. It's going to change it from greater than or equal to just greater than. You cannot write a test that would make this fail, because if it's equal to 100, it's already thrown the exception. Your test is hopefully going to capture that. But if it's equal to 100, it's never going to get to the second if statement. So this mutation is totally going to survive, and you're going to look at this and wonder, oh, maybe I should refactor that. And now it actually says what you're doing. So again, think of the mutants that survive may be actual problems that are going to damage consumers or hurt you in production, or they may be opportunities to refactor and make your code clearer and remove duplication or whatever.
And then there's the real problems. So, and this is things that the mutation tests catch. So we had one method in our benefit summary app, and it would call a different service, get some information back, and then it had to evaluate, and that's what this can convert method was. That just said, well, if it has a summary, then do some stuff and return that summary. And if it doesn't have a summary, well, go do some other thing and then return that. So, and we had some tests that tested some of these things, and it looked like pretty good code coverage. And then we ran this, and the mutation was it just inverted the Boolean, and the test still passed. So all of a sudden, we had a situation where it was entirely possible that someone could have made a change, just made a little mistake typing things in, and we could have gone to production. Thankfully, we didn't. We could have gone to production with this kind of change, and then some member calls our customer service team and they want to know this, that, and the other about their benefits. And the customer service person's like, well, you don't have anything here. And yet there is. The code has failed. So this pointed out to us, in this little area, our safety net is not very strong. So we had to refactor that. Similarly, and this was a Kotlin example. So we had another service that could look up a member based upon their phone number. And there are two end date cutoff possibilities. One is it could be a custom one, say, hey, look at my phone number as of X, or only going back a certain number of months. And if that wasn't provided, we just used a default 2 years. So the mutation test ran, and it inverted those. So that basically it always gave the default end date cutoff, because that always exists. That if is, and for those of you who don't know Kotlin, the question mark ... is just, it's like an if operator. So we had always went with the default. Now if we, again, same kind of thing, if a member had called and they provided an end date 2.5, 3, 4 years ago, we would have told them that we don't see anything here if our code had gone to production like this, because our tests didn't cover this. So again, this is an example of where our tests are pointing out real failures in our test suite so that we can go back and change those, and if necessary, then also adapt the implementation code.
I mean, the good news is that most of our APIs are not life or death things. So, I mean, but that's not necessarily true in all circumstances. If you need to be checking things, or if you're maybe working with a code base that does have more meaning, like if you can't find somebody's information based on 3 years ago, it's probably not going to totally mess up their life, but it's going to ruin their day. So that's not actually a good excuse. It's basically what I'm getting at.
Okay. So basically the majority of the surviving mutants were noise. Builders, getters, setters, custom stuff, just not very interesting at all, but worth looking at. There were a handful of refactor opportunities, either like we don't use this code, or there's extra machinery in here that we don't need or is not as precise as we'd like. And there were a small number of real problems in our code coverage that required our attention. But we hadn't known that they were there. So, doing it yourself. Here's the try it at home part. Yeah. All right, so these are the easiest ways to do it. IntelliJ and Eclipse have plugins. You can get them from the marketplace. You install them. They are really, really easy. It is literally you install them from the marketplace, you enable them. In IntelliJ, it even has a nice big pink run button that you will easily find. Highly recommend. If you're going to do it this way. If you use SonarQube, then that is a setting that I see a couple guys looking at each other nodding. Yeah, okay. It's a setting you can just toggle. You turn it on. Now again, depending on how long it takes for it to run, you may or may not want to do that every time or before certain builds, but you can do that. It's an option, and again, a pretty straightforward one. There's a Gradle or Maven plugin, 1 or 2 lines of code in your build file. Nice and easy. Pitest.org will tell you all about how to do that. There are other ways, importing some Gradle dependencies, a lot more difficult and bulky. We tried them. I recommend against it unless you have very good reasons. Start with the IntelliJ plugin or Eclipse plugin. Try the Gradle if that doesn't work, or if you don't have SonarQube, and then go into the weeds of all the other dependencies.
I also just want to point out the pitest.org symbol, canary with a miner's hat on it. I mean, I'm into logos. I think that's adorable. Okay, so if you're already doing TDD, you can make this part of your process. I probably would not recommend waiting until your API is 13,000 lines of code and doing it all at once that way. Instead, you could just incorporate it into your TDD process. So write a test, make the test pass. Maybe write some mutation testing or do some mutation testing on the code that you've just written, refactor the code as necessary, and start the cycle again. This might be most beneficial doing it in sort of blocks. So maybe don't run the mutation tests with every single piece of code that you write, but write a handful of tests, write a class or whatever, and then do a mutation test on that block. You can also make this part of your CI/CD pipeline. SonarQube, maybe we'll get to work SonarQube. I don't know. We have some trouble with bureaucracy in our organization getting that to work. But at some point, that would be part of our standard CI/CD pipeline. And it could be that every time we just push the code, it would do it. If you're going to run it on the entire API, maybe do that as a baseline. And then additional, as I said, additional code, you just do it in kind of blocks. So the conclusions that we've come to is mutation testing does its job. It reduces the risk of your safety net failing and you being unaware of those failures. It creates pressure to reduce the amount of code that you have and to reduce duplication. It makes the refactoring to make things more clear, that much more attractive because now you'll have fewer surviving mutants. It's easy to install, run, and to read the reports. The reports are super clear. And probably mutants will save the world. Here's how you can contact us. And any questions? We have
maybe one question.
Can you see the mutated code?
Yeah, I can show you a sample report. So I have this fake little fiddly API that I made. So this is,
you're not up there.
I'm not up there. Hang on. Can I get up there? I am in presenter mode. Yeah, hang on. I know how to work PowerPoint. Sorry, totally not up to him. That was me. Okay. Yeah, okay. So this is, and it is, sorry, it's a little bit off the screen, and it's probably really hard to read, but can I make that bigger? Oh, look at that. Yeah, so this is just a stupid API. I don't even look at this. My code coverage is terrible. But this is what the report looks like on my calculation service. And so you can see the green lines look like this. This is the code. And then down at the bottom, it shows you what all the mutations are. So this one has no coverage. And then if you hover over each one, it's here's what we did. This one wasn't killed by anything. It doesn't really show you literally what the mutated code looks like, but it gives you the line number and the kind of mutation it made. And so you just have to figure out kind of what it looks like. Yes?
Are the mutations random, such that if you ran the mutation test multiple times, you get different results?
Yeah, slightly different. I mean, we still got to, we ran them a bunch of times on the APIs that we work with, and they were similar results. In terms of the amount of getters and setters that we had and that kind of thing, but they were definitely on different lines of code.
So do you recommend doing them over?
Yeah, like I said, I would do them as part of your process, and I do think it would be good to incorporate it into your pipeline. Just know that it's going to take a little bit of time if you've got a big code base.
If QA, by example, as part of the CI/CD incorporates negative tests, how this solution can probably compare to that? Because a negative test, they have to program it like in Cucumber or whatever, and this is more randomized, right?
Yeah, okay, sorry, and I just realized we haven't been repeating the question. Yeah. So the question is, if in the QA process, if they're putting in specific values for the test and using something like Cucumber, I suspect, if that's part of an integration test, it's not really, this is not meant to be used with that. Our APIs, quite frankly, don't really have a front end, so we didn't run anything with that. The one that I'm making does, but it's super, super simple. But again, with the integration test, it's just not really meant for it. Yes?
Is there a way to forget about noise? If you run the same test over and over, it will always get the same noise?
The question is there a way, having identified some of that noise, if you can just avoid testing that stuff or avoid making mutations on it? I did not see a way to do that. You can exclude test classes, and you can choose which mutators you're going to use. So maybe you could tune it that way. But the kinds of things that we were seeing, like those getters and setters, That's not in the test classes, that's in the implementation code. And you can't really exclude implementation classes. You can only exclude the test classes. But I suspect maybe with some of the tuning on the specific mutators, you could minimize that somewhat. But you might also miss other things.
That was the interesting part about looking at all the noise is, I mean, yeah, most of it was just like, okay, not interesting, not interesting, not interesting. And you look at something, it's like, oh, all right, that's interesting.
Right.
I gotta fix that, or at least look into it further.
Yeah.
But yeah, you do have to kind of wade through a fair amount of like, yeah, nothing, nothing, nothing. Oh, okay, there we go. It's kind of like going to a garage sale that way. You know, you get you find that occasional diamond, you know, in the rough, but you got to wade through a lot of, you know, garbage. So, thank you.
Thank you very much.
All right, thank you.